All right, class. In today's video, we're going to be looking at a couple different examples of our information dealing with our distance and displacement, and then we'll look at one additional extension of that concept as well. So to start off, we're going to look through this quick example problem. So our job here is to figure out both the distance traveled as well as the displacement when a member of the St. John's track and field team runs a 100-meter dash as well as running a 400-meter dash. Now, this is going to kind of introduce something that's going to be a little bit interesting. So oftentimes, distance and displacement are kind of related to each other. But what we have, again, is there's going to be this key distinction between them when we think about whether or not the direction we travel in is important for calculating these two values. So if we think about, say, someone who is running a 100-meter dash, right, on the track, what they're actually doing is they're going from their starting point. They're basically running along the straightaway of our track. So we're basically running from point A to point B here. So we think about the distance we travel, right? Pretty straightforward. Our distance travel, that's just going to be the 100 meters of our race. When we think about our displacement, though, when we use this delta x to represent displacement, again, lowercase d, that's going to be distance. Delta x is our displacement. Right, if we're comparing our point A to point B, right, we're still traveling our 100 meters. That's going to kind of make up what we would call the magnitude of our displacement. But in displacement, we have to have a direction associated with it. So maybe we say our sprinter is running 100 meters going forwards. Maybe we're saying they're running to the right. Right, we kind of have a couple different options how we can describe the direction. But displacement, very important, does need to have a direction associated with it. If we then think about our runner who's doing a 400 is going to be one lap around the track. So let's say, again, they start off at that same point A. Now this time around, they're going all the way around our track. They come back. Again, finish line, it's going to be that same point. So when we think about distance, right, pretty straightforward. In a 400-meter dash or 400-meter race, they are running 400 meters. That's the total distance that they travel, the ground that they cover. The really interesting thing, though, is when we think about our displacement, though. Right, displacement is always showing us the difference between our starting point and our ending point. But in this case, the starting line and the finish line are the exact same. So we actually have no overall change in our position throughout the 400-meter race. And again, we get a displacement of 0 because our start and the end are going to be at the same location. So no overall change in position. And in the case of having displacement of 0 meters, we typically just ignore the direction, right? You'll travel 0 meters right or 0 meters left. You just go changing position of 0 meters. So looking at our next example question, we're going to have this car traveling along the Pennsylvania Turnpike. And our job now is we have information about its starting location, but we still want to calculate out our distance and our displacement. And now the last thing, kind of part C, we then want to know what mile marker does the car end up at. So first thing we can kind of do is just map this out a little bit. So they tell us that the far east mile marker is going to be mile marker 0. And going all the way to the west is going to be 300. So let's place mile marker 0 on the east side. Mile marker 300 is going to be on the west side. Now they tell us that our car enters the turnpike at mile marker 45. So marker 45 here, right? This is going to be our car's starting position. Oops. Maybe we call that our, again, point A that we begin at. And from there, we're told that the car is going to go 36 miles west. Again, west is, in this case, going to our left. So we'll go our .36 miles going west. We then turn and we come back 12 miles going east. From there we go an additional 23 miles east. Oh, sorry, 23 miles west. Sorry, that's going back to the left there. And then lastly, we go an additional 9 miles to the west. So eventually, part C, again, we're trying to figure out what is that mile marker we end up at. To begin, though, right, if we're thinking about trying to find the distance that we travel, right, total distance, total ground we cover, we're just going to add up each of our individual piece of motion. Now, because the car starts at our mile 45 marker, right, we're not assuming it's gone from 0 up to 45. That's just its starting position. So the 45 is not actually a distance we've traveled. So the first distance we actually travel is going to be our 36 miles going to the west. We then are going to travel our 12 miles going to the east. We'll then go our 23 miles going west. Then lastly, we're going to go our 9 miles going west. So when we add up each of these individual legs of our motion, our 36 plus 12 plus 23 plus 9, that's going to give us total distance traveled of 80 miles. In part B, for our displacements, again, the thing we want to do is decide which direction is positive, which direction is negative. So since going west is increasing our mileage, let's make going west our positive direction. That means anytime we go east is going to be our negative direction. So our first piece of motion here, we're told we're going to go 36 miles west. So 36 miles west is our positive direction. From there, we then go 12 miles to the east. Again, east is negative direction, so we'll subtract 12. From there, after our 12 miles east, we go 23 west. So 23 west is in the positive direction. So we'll add 23. Then lastly, we're going to add the 9 for our 9 miles west. So positive direction again. So if we take 36, we subtract 12, we add 23, we add 9. That's going to give us a positive 56. Now, because we have a positive value, right, means we've gone in our positive direction. That positive direction we're calling west. So we can say our overall displacement is going to be 56 miles going west. So when we think about the mile marker that our car ends up at for part C, right, basically what we're saying is if we start off at mile 45, so mile marker 45, that's our starting location, we then go an additional 56 miles to the west. If we add 45 to 56, that means that we're going to end up at mile marker 101 as our final location. So what this means is, right, if we think about where we're moving along our number line, if we go start off the 45 mile marker, and then we add 36 to the west, subtract 12 to the east, add 23 to the west, add 9 to the west, we're going to end up at mile marker 101 as that final position. So as this takes care of the distance and displacement scenarios we're going to be looking at, we're moving in what we call one dimension. So, right, we're only going forwards, backwards, we're only going east and west. Now what we're going to do is look what happens if we're going, say, both forward and backwards, but also going right and left. So the scenario that we're going to be working on is we have a car that's going to be driving 18 miles going north. So what that looks like is we first go 18 miles north. We then turn and then drive 5 miles to the west. So our job again is to figure out both the distance our car travels as well as what we're going to call the magnitude of our displacements and the direction. So to do this, what we're going to have to do is think a little bit about how we can kind of work with these vector quantities. So first thing, if we're trying to find distance, right, we said distance was going to be a scalar quantity. So all we want to do is add the lengths of our individual movements together. So for this case, right, if we're trying to find our total distance traveled, we're basically just saying we're first going 18 miles, and then we're going 5 miles. So our 18 plus 5 is going to give us 23 miles for our distance. Again, distance normally the easier the ones to look at. Our displacement though, our displacement is, it's a vector, so basically an arrow that's going from our starting point to our ending point. So we come back up to our diagram, right? Our starting point, that's going to be, let's say where we began, let's call that point A. We went 18 miles north, we then went 5 miles west. We then end up at point B at the end here. So our displacement vector is basically this arrow, the straight line that's connecting our point A to point B. That's going to be our displacement. So the first thing we'll look at is what we call the magnitude of our displacement. Right, this is basically just saying what's the length of the arrow. So it's basically looking at what's this straight line path to get from our point A to point B. So to do this, we're going to have to use a little bit of our geometry using our Pythagorean theorem. So in all these, we're going to be making what we call right triangles. Again, every right triangle is going to have a 90-degree angle one side, and basically what we have is that the side that's across from that 90-degree angle, right, that's what we label C, that's going to be our hypotenuse. And then our other sides we're going to call A and B. So what our Pythagorean theorem says is that A squared plus B squared is equal to C squared. And our job here is if we can solve for C, that value for C, that's going to be the displacement of our object. So let's say if we were to apply this to our object that's we're trying to figure out in part B what our displacement is. Right, so we're saying if we go our 18 miles going north, we then have our 5 miles going west. Again, we're trying to figure out as we go from point A to point B, we want to know what that length is. So using our Pythagorean theorem of A squared plus B squared being equal to C squared. Again, we're looking at the 18 and the 5, right? Those are our two sides, A and B. It really doesn't matter which one we call A, which one we call B. So let's just say, let's make 18 is going to be our side A. The 5 miles is going to be our side B. So we have 18 squared plus 5 squared is equal to C squared. If we square 18, that's going to give us 324. If we square 5, that's going to give us 25. Again, all being equal to C squared. So 324 plus 25, that's going to give us 349. Now we're almost finished, but right now we have 349 is equal to C squared, but we're worried about just that length C. So to solve this for C, what we want to do is we're going to have to square root both sides of this equation. So if C is equal to square root of 349, our square root of 349 is going to be 18.68. So if we think all the way back up to our original question, right, what is the magnitude of our displacement? So the magnitude of our displacement, that's going to be our 18.68 miles. The last thing we then have to do is figure out our direction. So in finding our direction, what we're going to do is basically think about our compass rows here. So let's say we have our standard northeast, south, and west. So we have northeast, south, and west. And just to be a little bit more specific, what we're going to do is we're going to break these quadrants up in half. So we're going to add in this line that's splitting north and east. That's going to be our northeast line. We'll have the same thing. We'll have a southeast line have a southwest line. And lastly, we'll have a northwest line. Now, our job is basically to figure out of these kind of 8 little quadrants or spots, which one are we going to fall into? So the way that we do this is if we were to look at, say, this region in here, basically what we have is if we are in between east and southeast, right, anywhere that we're in here, maybe we're going in, like, let's say, that direction here. In these cases, we're going more east than we're going south. So we would call anything in here, we would call this east of southeast. Again, we've gone more east than we have gone south. If we're in this section, though, of that quadrant, in this case, what we've done is we've done more, traveled more to the south than we have gone east. So we would call this south of southeast. So thinking back to our direction here, right, we know we've gone north and west. So our direction, we know we've ultimately entered into this kind of northwest quadrant for that red arrow from point A to point B. But because we go more north than we go west, right, if we're comparing 18 and 5, right, because we're saying 18 is going to be bigger than 5, that means we go more north than we go west. So we would call this then north of northwest as our direction. So our overall displacement is going to be 18.68 miles. Again, direction will then be north of northwest. Again, if we had instead say maybe we went more east than we did north, if we went more west than we did north, then we would be traveling west of northwest. Here again, we've got more north, so it will be north of northwest.